That's very bright. Okay, can you guys in the back see the board? Is it? All right, so let's get started here. So on Wednesday we talked about how to name the different carboxylic acid derivatives. Today we're going to be going into how to make them and possibly the reaction they participate in. Most of these reactions are things that you already know, so you know they're all interconnected. It'll be a review kind of thing. But first, let's talk about the factors that affect the reactivity of the carboxylic acid derivatives. So if you have, there are two basic factors that we'll be looking at, steric factor and electronic factor. So if you have a carboxylic acid derivatives of the same series, okay, let's say you're considering esters, or you're considering acid halide, or you're considering amide, or whatever group you have, okay, they are of the same series. Steric factor plays a huge role in how those derivatives will react. Because we said the reaction they undergo is nucleophilic acyl substitution reaction, okay, they undergo nucleophilic acyl substitution reaction. So that means your nucleophile has to be able to approach your carbonyl carbon in each case, right? Your nucleophile has to be able to approach that carbon. So the steric crowdiness around that carbon plays a huge role in the reactivity of those functional groups. So the less substituted that acyl group is, the less crowded this carbonyl is, the more reactive it's going to be in each series. Okay? The more crowded it is, the less reactive or the less easily accessible that carbonyl carbon is going to be. Okay? So if you consider an unsubstituted, okay, so this is the alpha, you're looking at the alpha carbon to the carbonyl. If you have an unsubstituted alpha carbonyl, so basically you have hydrogens, that will be the most reactive in any of this series. Okay? Then if you change the substitution to 1, that decreases the reactivity, and change it to 2, it's even slower. When it's tri-substituted, it's the least reactive. So the reactive of any of the derivatives depends on the steric factor at the alpha carbon. It could be alpha, it could be beta, you know. But if it's farther from that, it's not going to have affected that much, right? So the steric factor is only going to have effect if it's very close to your carbonyl carbon. Okay. So the second factor is electronic. So the electronic factor can compare the reactivity of the derivatives across the different types that you have. Okay. So the least reactive is going to be your amide. Why is it the least reactive? It depends on the stability of the corresponding anion of those circle functional group that you have connected to the acyl group. Okay, so the when the functional group you have connected to the acyl group, so let's, as a reminder, that is the acyl group. When the functional group you have connected to the acyl group is a very good leaving group, then that carboxylic acid derivative is going to be very reactive. So the best leaving group out of all these functional groups you have connected to the acyl group L will be the halogens. Okay, because they are very stable. The corresponding anion is very stable as compared to the anion that you get if you expel this. So if you expel the functional group you have connected to the acyl group in amide, it's going to be NH2 minus. NH2 minus is not stable. It's a very strong base and a very strong nucleophile. So as soon as it comes out, you want to add back in. Okay? Whereas the chlorine is happy to be Cl minus. Okay? So that's why the reactivity increases as you go from amide to acid chloride. Ester is, the alkoxide you get from here can be isolated, right? So that will be the leaving group that you have there. Okay. In the ester, the OR minus, which is the alkoxide, is also stable, right? So it can act as a very good leaving group. Thiol-ester is even more stable, so it's a better leaving group. And the carboxylate is also a very, very good leaving group. So that will be the leaving group you have in the anhydride, whereas the chloride, very, very stable. So the most reactive of all your carboxylic acid derivatives are acid chloride. Okay? So R could be anything, right? So if you're given, in an exam, if you're asked to compare the stability or reactivity of these functional groups, it doesn't matter what R is when you're looking at the electronic factor. Okay? You want to look at this leaving group first before you consider what is on the R groups. Make sense? Does it make sense? Okay. Just to deviate a little bit. However, let's just give an example. Let's say you have
Can you look picture?
okay, so let's say you ask to arrange this in order of reactivity. Okay, so the most reactive to be 1. Okay, so let me just say this is A, B, C. Okay, the most reactive is going to be 1. So which of the 3 will be the most reactive? C. What will follow?
A.
So by the leaving group A, they'll be almost the same, but because you have chlorine here, which is an electron withdrawing group, it's making this carbonyl to be more reactive, correct? Because it's withdrawing electron from the carbonyl. If you go back to reactivity of carboxylic acid, right? So the closer you have electron withdrawing group to the carbonyl, the more reactive it's going to be. The same effect of this electron withdrawing group on this carbonyl. So it's making this carbonyl to be more electron deficient, so your nucleophile can add in, even though this is a very bad leaving group. Okay? So the rate at which this will leave will be the same, except the carbonyl is going to be more reactive in this case. So that means your nucleophile that is trying to come in will be able to attack A faster than it will B. Make sense? Yeah.
So you said consider the electronic factor before the steric. So if that Cl was like a CH3 whatever, then you would be.
Yeah, but remember that this is not alkyl. So this is also inducing some electronic effect, right? The alkyl group is both deactivating the carbonyl by inductively donating electrons. So its steric factor overrides its electron donating ability in that case, because either way it's making it less reactive. Whereas this, even though it's a little bit crowded, inductively is withdrawing electron from the carbonyl, thereby making this carbon to be more reactive. Okay? Make sense? All right. Okay, so let's now talk about how to make them. How do you make the derivatives? Okay, so acid chloride. If you want to make acid chloride, depending on the structure, all you need is titanium chloride. That is your chlorinating agent. So if you're making your reference card, that might be helpful. Chlorinating agent in this case. So it's going to convert the OH functional group to chlorine. So that's easy. Okay? Now the same thing is true for this guy. So the OH functional group there will be converted to chlorine. If what you need is acid bromide, then you're going to be using PBr3. Okay? So this will convert the OH functional group you have there to Br. Right? And the mechanism is by nucleophilic acyl substitution reaction. So it's a substitution mechanism, just like we have okay, so let's take this as an example, acetic acid, and you're treating it with titanium chloride. Okay. So your carbonyl oxygen is more nucleophilic, so it's going to attack the sulfur. This oxygen carbonyl will break. You have an intermediate. Sulfur. I'm going to put this over the stuff over there. That's messy, but bear with us. It's chlorine. So this is not positively charged. Okay. So this is going to reform the carbonyl type structure back, and the halogen will leave. One of the halogens will leave. So you have sulfur, oxygen, plus of H, chlorine, and then you have the Cl minus that left. Okay, so this Cl minus is going to act as a nucleophile. You apply this carbonyl carbon, this will break. Okay. Now the chlorine has been added here. Okay. So this is now make this whole group a very good leaving group. The carbonyl will form. This will form a double bond with the sulfur. This will break. Okay. So you're going to have, now what do you have? Now you have, let me draw the two stuff that you're going to have there. Stuff here. Now you have this chlorine. This is now double bond with oxygen. The hydrogen is still in there. You have a positive charge on the oxygen. So plus this oxygen has now formed a double bond with the sulfur. This is OH, O minus, and it has the chlorine there. Okay. So this will form a double bond kicking out the chlorine. Okay. So you'll have this plus your protonated acid halide and plus Cl minus. Okay, so that Cl minus will pick up this hydrogen for you to get the free acid halide. So SO2, which is gas, plus HCl, plus okay. That's how that forms. Alright. So that's how to make your acid halide and the mechanism. Now to make acid anhydride, you can reflux at a very high temperature 2 carboxylic acid together. That will lead to elimination of water. Okay, that's how you get the water, and the remaining molecules just join together to create acid anhydride. Okay, so that's very straightforward, but you need a very high temperature for that. To make esters, you can react your carboxylic acid with your alcohol under acidic condition. So this is a catalyst. It is called Fischer esterification reaction. And what you get as a result is basically the way to imagine the product is changing this group with whatever group you have as an alkoxide of your alcohol interchanged, right? And your product is going to be that. Okay, so this alkoxide replaces the OH functional group that you have connected to your carboxylic acid, and you get your esters. Now, in esterification reaction, all the steps are reversible. So we're going to look at the mechanism for that. We're going to look at the mechanism for that. So you need acid catalyst for the reaction to proceed. And why do you need the acid catalyst? You need the acid catalyst to activate. Remember we said the OH functional group in carboxylic acid is a very, very bad living group. This is a very poor living group. Okay, so that's why you need the acid catalyst. That's why you need the acid catalyst. So what's the mechanism? Well, the first step is activation of that carbonyl with your acid. That's your first step. So it's your carbonyl oxygen that is going to pick up the proton, not the alcohol that you have there. So this now becomes activated carbonyl. Okay. Now your alcohol can come in. Your nucleophilic site is the oxygen in the alcohol, which is going to attack the electrophilic carbon of the carbonyl, breaking up that carbonyl double bonds. So now you go from sp2 iodized carbon center to sp3. So this is now H. This is from the ethyl, from the ethanol, and that's the OH functional group that was on there. Okay, so 3 bonds around this oxygen, so there's a positive charge there. So the next step is going to be proton transfer. So this is going to pick up the proton, that goes back onto the oxygen. So now you have okay. So your carbonyl double bond will reform, and this water molecule will be kicked out. I would say they're all reversible, so at this point you have okay, of course, plus your water molecule that you kicked out. So this water molecule is going to act as a base now to remove that proton and get your free ester. Plus the acid you started with. So that's why the acid is a catalyst. So that's the mechanism. Okay. All right. So let's look at an example. Oh, did you guys, were you able to get that? Okay, can I move it?
Yeah.
All right. So let's look at an example. How will you prepare the ester below from its corresponding carboxylic acid? So, very easy to predict. Here's the trick. When you're given an ester, and you want to break it down to the corresponding carboxylic acid and the alcohol that you use, just circle the acyl group and then circle the alkoxy group. Okay? The acyl group forms your carboxylic acid and the alkoxy group forms your alcohol. So that means the starting material you will use for this will be plus okay, because you remember you're eliminating water when you do esterification reaction. So basically when you do esterification reaction and you react the acid, well, the organic acid with the alcohol under mineral acid condition, water is going to be expelled, so you have to find a way to get rid of that water, otherwise it's going to react with your ester and go back to the carboxylic acid. That's why the mechanism shows that all the steps in there is reversible, right? So how do you circumvent that when you're doing an experiment in the lab? We use what we call Dean stack. Okay, so basically a Dean stack, I'm going to come back to this question. So a Dean stack, so basically what does that mean? Well, you had your reaction flask. I'm not an artist, sorry. Okay, you have your reaction going on in there, and you connect how do I do this? So you connect another, okay, so let's start from here. You have this tube that has these hands connecting to your glassware. So there's an opening there. And then you have a condenser. Your condenser, right? Sorry. You have your condenser, right? So when the vapor is going up here into the condenser, it will be coming back down through the walls, right, of the condenser, and some of it will be going here. So whatever solvent you're using in your reaction, you're going to put that same solvent here. So let's say you're doing the reaction in, I don't know, maybe hexane. Not hexane, well, okay, let's say hexane. Okay, let's assume you're doing the reaction in hexane. This is going to be hexane. Okay, so as the vapor forms and rises up, and the water is trying to leave the reaction with your alcohol, because the alcohol also evaporates. So both will be turning into vapor rising up, and through the walls they'll be coming over here. But because you have hexane here, the water that you have is denser than hexane, so it's going to go to the bottom, pushing the hexane to the top. So hexane will be coming back in here. So this will be trapping the water at the bottom. So that's how you get rid of that water in the reaction, so that it doesn't interfere with the product you're forming. Okay, so that is Dean stack. Another way to get rid of it is to put molecular sieve into your reaction mixture. So molecular sieves absorb water. Okay, so as soon as your water is formed, yeah, you have the picture there.
Yeah, you know, you're trying.
Yeah, I'm not a good, the concept is what we need, right? So this is how Okay, so this is how the Dean stack looks like. I tried, right? Okay, so you have your reaction going up there, it rises up, this is a condenser, so the vapor condenses, try to trickle down, come back down, goes through this wall, in here, well, sorry, goes in here, and then you have the solvent that you use there. Water goes to the bottom because heavier pushes the solvent, all the solvent comes in here and the reaction continues. So you can actually measure, if you calculate using the stoichiometry of the reaction, if you calculate the amount of water that should be produced, you can actually monitor the progress of the reaction by the volume of water that's collecting in here. Okay? So it's kind of a, thank you for that. I tried, right?
It was really close.
Well, yeah. Alright, so that's how Dean stack looks like. Alright? So that's why the mechanism says the reaction is reversible, because if you have water in there, it's going to hydrolyze your ester back to the carboxylic acid. Alright? So the question, back to the question. Why is it? Something is wrong with this.
The light's not on.
Anyway. Okay, so back to the question. So the carboxylic acid you start with comes from the acyl group, and the alcohol comes from the alkoxyl group, okay? But you're not done, because it says how would you prepare it. Now you've listed the starting substrate. Now you do the reaction. Okay? So you're going to write base acid plus the alcohol with acid catalyst to get your ester. So esters are nice smelling compounds. We synthesize those in the lab. So okay, so that's one way to make esters through esterification reaction. Now another way to make ester so this is making ester from carboxylic acid. Another way to make ester, I'll write that somewhere, is another way to make ester is by reacting your acid halide, in this case acid chloride, if you want to get the name, so that is acetyl right, because we've learned how to name them. So when you treat base with the corresponding alcohol, so for the example we are considering, if you treat that with corresponding alcohol, you can conduct nucleophilic acyl substitution reaction with that to get you your ester. Okay. And this still falls, bless you, this still falls into the retrosynthesis that we had over here. I'm going to put it back on. That you first identify the acyl group, and then you identify the alkoxy group. The alkoxy group is going to be your alcohol, but your acyl group will either be your carboxylic acid if you're using Fischer esterification, or it could be acid chloride. So that means or. Okay, so those are the two methods to make this. Any question? Okay, so that's nice. All right, so how do we synthesize amide? or amide, however you want to call that. All right. So you may think that it's easy to let's say you were given this amide and you're asked to make the amide. You can do the retrosynthesis that we use for the ester. So you identify the acyl group and then you identify the amino group. So that's an amine. Okay? And break them into two. So you have the acyl counterpart with the amino group. So we have to, since this is 2, we have to make this 3, right? Okay, so it's an amine with an acyl group, but this acyl group could either be, based on what we did for esters, this acyl group could either be OH for carboxylic acid or could be acid chloride, right? So in this retrosynthesis, you will not be able to use carboxylic acid. Why? Because it's a carboxylic acid and the amine is a base. So if you treat an acid with a base, you form salt and water. So if you're trying to make these by treating carboxylic acid with the corresponding amine, what you'll be getting is a protonated amine. It will be like adding HCl to your NH3, which will give you NH4 plus, right? Cl minus, correct? So if you use organic acid and you treat it with amine, what you will get is a salt. So it's not going to give you the amide that you need. Okay? So reacting this amine, which is an organic base, with a carboxylic acid, which is an organic acid, is just going to give you an ammonium salt. So you won't get your amine and you won't get your amide. That's not going to work because the nitrogen is going to pick up the proton of the acid and the reaction will stop there. To circumvent this problem, the third reagent is needed in reacting these two things together. And that third reagent is called DCC. Dicycloacyl carbodiimide. That's the structure here. What is the similarity between these and what you want to use? What is common to these and that? Huh? Yeah, don't second guess yourself, be bold. Yeah, you're right. Don't doubt yourself. Yeah, what is common to them is you have nitrogen here and you have nitrogen here. It's like, yeah. I know what you are all thinking about is you're looking at the R group and you're looking at the whole structure you have there and you're like, there's no similarity. That's not what you should be doing. When you're conducting a reaction, you're looking for the reaction site. What is the reaction site? The reaction sites are the atoms that you have in the structure. Okay? So when you look at when I ask the question, what's the similarity between these and these? The only thing that you can see that is similar is this atom nitrogen and that atom, those atoms nitrogen. Okay? So yes, it's the nitrogen that is similar. So whoever designed this reaction thought about, okay, instead of me using the amine that I need, which is going to be protonated and won't give me the amide that I need, let me use another stuff that has nitrogen in, that can pick up that proton. Okay? It can pick up that proton from the carboxylic acid, therefore this is not going to pick up the proton. And then when that proton is off, this can now act as a nucleophile instead of acting as a base to attack the carbonyl carbon. So usually when you want to do this reaction in the lab, you premix your acid with the DCC so that the protonation occurs before you throw in your amine that you need. But we're not doing this in the lab, we're doing it on the paper. So we can just write your carboxylic acid plus your amine with the DCC, and that will give you your halide. But if you don't put that DCC in there and you draw your amide, it's going to be incorrect. Okay? So just remember DCC, like PCC, right? Okay. The mechanism, yeah, I can show you the mechanism, but let's keep that. Okay? Alright. Alright, so that's about, I think we've talked about all the, with the exception of phosphate, we've talked about how to make acid halide, how to make esters, how to make anhydride. Okay, how do you make an anhydride? You remember that? Let's recap. How do you make an anhydride? Let's just quickly recap what we've done. I'm going to stop there. But let's recap what we've done, right? 2 carboxylic acid, correct? So if you want to make an anhydride, you react two carboxylic acid together under very high temperature, and you get your anhydride. Yeah. Okay. What about if you want to make? Why is it? Well, we're done anyway, so that's good. So what about if you want to make? So this is anhydride, correct? So this is the mental game you should be playing at the end of every lecture, right? So try to remember what we've talked about. So what about acid halide? Let's say you want to make acid chloride. How do you make that? With what? With the carboxylic acid, right? So you take the corresponding carboxylic acid that you need, whatever it is, treat it with SOCl2, and it will give you. Well, what about if it's a bromide? What do you use? That's correct. Okay, if you want to make esters, how do you make them? Esterification reaction, right? So you could use, so what do you esterify? The carboxylic acid with the alcohol that you need, correct? So R and R prime could be the same. And you'll get, so this will be R or R prime. Is there any other way to make esters?
Yes.
From acid halide, correct? So you can use acid halide with the alcohol. So this will not be reversible. Okay, so you get your ester. Okay, so what other functional group did we talk about? The last one. Amide, right? And how do you make that?
DCC.
Yep. So you need your carboxylic acid and your amine that you need, whatever that amine is. But the key reagent there is the DCC for you to get your okay. So what we did in 1 hour, we actually summarized in like 3 minutes, less than 3 minutes. Okay. So when you're making your reference card, this is all you need to put there. You don't need to jam your reference card with different structures, different. It's very, yeah.
Is there a way that you can put the amide reaction on like the mechanism, because the book does your reactions different than you do in class?
How do you mean the book does reaction that I do in class?
Like the way that you were preparing the acid chloride. I mean, the first reaction, it was different than in the book.
No, it's the same. So that's the problem McMurray has. It keeps so many intermediates, right? McMurray will say, let's see, which one are you talking about? This one?
The one with the associate, yeah.
Yeah. So what McMurray does, that's a good question. I think I have extra paper somewhere here. Here's what McMurray will do. It will skip every step that you have in between and say, watch this. So it's going to attack this, break that, bring this back and keep this out, and just give you that intermediate that you have, correct? Is that what it does?
No. For the book, it doesn't attach the SCl to the double bonded one. It attaches it to the
To this?
yeah.
No. Well, yeah, so it skipped, this is what it did. It skipped this up to this level. Okay? So McMurray skipped so many steps, and which is one of the reasons we're thinking of switching from McMurray. Because we want students to really understand details of mechanism. So whatever I give you is fine. Whatever they give you is also fine. It's just incomplete. It's not like it's incorrect. It's just incomplete. So usually when I'm breaking the mechanism, I'll look at each set. I'll look at each arrow. So if you combine all the arrows together, I'll just give you credit for it, even though you're not showing the intermediate, unless I specifically say show all the intermediates. All right. So we'll stop there. I hope you have a nice weekend. And yeah.
Dr. Deli?
Yeah.
Is your office hour now or 11?
I don't have office hours on Fridays. It's Monday through Thursdays. But if you come, I will attend to you.
Now.